Aha! We're back, part 2 of analyzing situations involving friction. Part 2 is a little more complex. We're going to deal with an angle, but we'll be able to tackle that very easily with the stuff we've already learned. Just a little bit of trigonometry. Piece of cake, guys. So if you've tuned into this video first, this is the second one. And the other one you should watch first, unless you're so advanced and like, that's cool. You can just go ahead and continue watching because maybe you'll just get it the first time with the angles. Situation's kind of similar. Anyway, we have our kitten in the crate, and it's being pulled with 120 newtons, yum, 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 at an angle of 30 degrees with respect to the horizontal. That's what WRTH is. It's not a radio station, it means with respect to the horizontal. The coefficients of friction, static and kinetic, are the same as they were before. So it's 0.5 and 0.25 respectively. And we'd like to determine the force of friction in each case for static and kinetic, and still the acceleration, the mass is the same as it was before, 10 kilograms. Our relationships are the same. Force of friction static equals mu static times force normal. Totally the same. We'll just have to address that angle. Force of friction kinetic is mu kinetic times force normal. Again, same deal, but we have to take care of that angle. The next thing we do, create the free body diagram. So with the free body diagram, again, I've established my coordinate system. Up is positive, right is positive for the horizontal piece. We've got our kitten mewing about, and yes, still doing its thing on top of the crate. But now the difference is we have the force applied at 30 degrees. So this 120 newtons is now being pulled at 120 degrees. So that's going to have an effect on our system, and we'll see that in the free body diagram in just a moment. We have the sum of the forces in the x direction horizontally is equal to mass times acceleration in the x horizontal direction. It's still Newton's second law, but now we've got to deal with that angle. Piece of cake again. Sum of the forces in the y direction equals mass times the acceleration in the y direction. Same deal. But if this thing still has a normal force, this is still easy in that there's no acceleration in the y direction. So that's kind of key. And we'll find out what happens. Okay, here's the free body diagram. Really, really key. Very, very important to create these. So force applied is at 30 degrees. Our force of friction is completely horizontal. It's always in the direction of the motion. If the motion is right on the surface, force of friction doesn't change that angle, so it's going to be horizontal parallel to the motion on the surface. Force of gravity is down, force normal is up. The difference now is that we have a different force applied in the x direction. It's a component, the x component of force applied, and the force applied in the y direction is the component for the opposite side of this triangle in the vertical direction. So force normal is affected because it's not the weight of the system any longer. It's going to be the weight, but some of that weight is being removed because the force applied y is in the upward direction. So if you remember the bathroom scale demonstration, or remember back to the chupacabra notice bien, that if there's an upward force pulling the system up from that surface, Newton's third law says less force is going to be applied to that surface in response, so force normal will go down. We'd expect that it's going to be less than the 98 newtons it was last time. In the x direction, we'd also expect that this force is less than 120 because some of it is being translated into that vertical pull. Therefore, over here, it's going to be less than 120. It's only a component, so we'll see how much it is. So let's actually do this. All right, let's start with the x direction, since that's over here. So let's sum the forces together. We have in the positive direction force applied x, so force applied x. In the negative direction, we've got the force of friction, both static and kinetic for different cases. All right, now the thing is, what is that? Well, we look over here, and based on this triangle, this is the adjacent side, so we have the hypotenuse. Therefore, this is nothing more than force applied times the cosine of 30 degrees. All right, so that makes it a little bit less, okay? How much is it? Well, cosine of 30 degrees is actually 0.5 if you type that into your calculator. And so really the amount of, no, sorry, it's not 0.5, that's the opposite side. It's something else, like 0.866 or something like that. So again, this guy over here, if I take 120 times cosine of 30 degrees, actually it's about 104 newtons. 104 newtons. I just confused the sides for a moment, but good bookkeeping means that we figured out what our situation is. Okay, force applied cosine of 30 degrees, which is only 104 newtons, minus whatever the force of friction is. And that equals, yes, mass times acceleration in the x direction. So we'll figure out what that is on the next page. Let's go to force in the vertical direction. So we've got the force normal. We also have in the positive direction force applied in the y direction and minus force of gravity. All right, and that actually equals 0 because, again, if this is going to be on the surface, then that has to be 0. The only way we have a force normal, again, is if there is something resting on the surface. It so happens, though, if this force is too high, if I pull up at a high enough angle, I may lift the entire crate and kitten system off the ground, and there's no more normal force in that case, and so there's no friction. You need a normal force. You need the interaction between the nubblies on the surface in order to have friction. So we'll have to make sure, though, that the force applied y isn't greater than the weight, because if it is, then it's going to be lifted up off that surface. But I kind of know it's not because I did this problem before, so it should work out. Let's take a look. Okay, force applied y. Well, let's look at this part here, and that is going to be related to the opposite side, which, therefore it's the hypotenuse times the sine of the angle. So we've got force applied times the sine of 30 degrees, like that. Here, I like doing this. Yay. Okay, the sine of 30 degrees totally is 0.5, so I've got 120 here and 0.5 over here, and so this whole term is 60 newtons. So let's take a look at what's happening over here. All right, so I've got force normal, which I don't know yet. I've got force applied y, which is 60 newtons, and the force of gravity, which is 98 newtons, but this is negative over here. So this becomes force normal minus 38 equals 0, and force normal would then equal 38 newtons. Okay, so if we do this out and solve for force normal, subtract, let's see, minus force applied y plus force of gravity, all on the other side of this equation, and force normal becomes 38 newtons. All right, let me get out of the way so you can grab all that stuff down. Again, that came from the upward pull at that angle. The 60 newtons here takes away from the weight on the surface. Therefore, solving for force normal gives us 38 newtons. Okay, so we're on to that last step. And so this will look familiar as well. Boom, boom, boom. All right, now our difference is that our force applied was 120 newtons. Our force applied in the x direction was 104 newtons. Force of friction static is mu static times force normal. It's 0.5. That didn't change. That was still the same rating. Mu doesn't change, but the force normal did. It was only 38 newtons, giving us 19 newtons of force of friction static. So a lot less than before, where we had a considerable amount more, 49 newtons. It's much, much less. So the crate will not move unless force applied x is greater than force of friction static. Okay. Well, we found force applied in the x direction to be 104 newtons. It was 120 times the cosine of 30 degrees. And yes, it's definitely above the 19. So even though that resistance is less, and also this is less, it's way more. The force applied in the x direction is still way more than the force of friction static. Therefore, it's going to be in the kinetic region, and we'll see if it accelerates. All right. Force of friction kinetic is mu kinetic times force normal, 0.25. That hasn't changed. That's still the same. because it's the relationship between two surfaces. 0.25 times 38 is 9.5 newtons. Okay, so force friction kinetic is only resisting with 9.5 newtons. We have 104 newtons now in the horizontal direction instead of 120. Let's see what happens. Everything is the same here as it was before. Again, that only change was, dealing with the angles. So we got the force of friction in the sum of the forces in the x direction equals ma. Solve for ma. Sum of the forces in the x direction divided by m. Okay, that's force applied in the x direction minus force of friction kinetic, and divided by mass. And what we got here is 104 minus 9.5 divided by 10. So that's actually 94.5 divided by 10. The acceleration now is slightly less, and it would change as a function of the angle up until the point where you're actually pulling up with so much vertical force that you might lift the object right up. So anyway, this is 9.45, less than 9.55. So a little bit different than before, and the units are still meters per second squared. So the acceleration is 9.45, and it would change as we would increase the angle even more. So up to that point where it would be lifted off the surface. All right, there it is. We took care of the angles using sine and cosine, depending on if it was horizontal or vertical. That angle was with respect to the horizontal. It's really key to keep track of that. We'll be doing something called an inclined plane, where we may take a different angle reference. We might take one with respect to the vertical because it's more convenient to do so. But for now, we took it with respect to the horizontal. So, all right, we did it with the angle. So these two things, we discovered there was a bit of a difference in the acceleration, a lot difference in the forces that were necessary in terms of friction, a lot less, but because the force was being translated a little bit more vertically, the acceleration actually went down, which is kind of interesting. All right, that's what it is. We've done these two problems. Good stuff. Morad, out.